continuing from the last lecture, I just want to add or emphasize certain things regarding groups, that no element of the group will be repeated in a row or a column of a group multiplication table. And let us take one simple example of a group of order 3. So, a group of order 3 would have basically 3 elements in it. One, of course, has to be the identity element and 2 other elements, and it will have some combination rule. This combination rule could be anything. Let us try and build a group multiplication table for this simple group. Now, of course, clearly I can fill the first row and the first column. Identity followed by an identity would be identity. Element A followed by identity will be A, and so on. It will be, this will be B. Same thing happens in column. This time identity followed by element A would be A, and then the next one would be B. Now, we are left with only 4 cells to fill. Now, I do not know what the combination rule is for this, whatever it is, as long as I am assured that this is actually a group. So, in this particular row, A element is already there, therefore, I can only put the element B or 1 in the 2 cells of this row. Now, element B, can I put here? I cannot, because there is already element B in the column, and hence we cannot put B here. Therefore, the only place where I can put this element is in this location. Now, only one element is left, which is the identity element. So, 1 has to come here. Now, come into the second row, second column. A and B are already there, only element 1 is left. So, 1 has to come here. Similarly, if I come to this column, B is there, 1 is there, A is not there. So, A has to come here. So, there is only one way that this group multiplication table can be filled, regardless of what the combination rule is. So, I will just repeat that no element in a row or column can be repeated. So, this is a unique, in this case this becomes unique. If I take a 2 element group, which is a group of order 2, the same thing, it will be unique. If I consider a group of order 4, so I have 4 elements here. Now, there are only two ways that a group multiplication table can be filled. And of course, once you go to higher orders, there are more different ways are possible for the group to operate depending on what the combination rule is. So, the important thing is that this is the thing that we should remember, and this will greatly facilitate us in developing different groups when we are going to talk about now symmetry groups. So now let me come now directly to groups which have only symmetry operations in them. So let's take some groups now, groups of symmetry operations. So let's take first a simple one, starting with, or rather two of them. Let's take only a two-fold rotation symmetry. Now, two-fold rotation symmetry would imply essentially it will have only two elements. All groups have to have an identity element. So, it will have an identity element and it will have an 180-degree rotation about some point A. Another group that I could consider is the presence of a mirror, reflection symmetry. Now, this again would have only two elements, the identity element and the reflection operation, which is denoted as sigma. Now, I could very quickly geometrically visualize these two groups, and then later on we will have more discussion. So, geometrical visualization could be seen like this. Let us try first of all a two-fold. So, I have a two-fold rotation axis at some point A, and this dotted line I am just drawing as a reference, and I use in order to geometrically visualize it, I will use a asymmetric object that I have been using earlier as well, the letter F. When rotated through 180 degrees, would reposition itself here. Now, this is a geometrical visualization of this particular group. The second group that we can visualize is the presence of a mirror. So, mirror I will denote it as a solid line, and again I make use of this letter F, which is an asymmetric figure, and its reflection through the mirror. So, these are two different groups in which I have done this geometrical visualization, and I want to just dwell a bit on why I have chosen this particular object to visualize this. So, this symbol F is asymmetric. In the two-dimensional plane. We are talking about only two-dimensional symmetry right now. And hence, one of the properties of this symbol is that this is also a chiral object. Now, what are chiral objects? Well, chiral objects have the property of handedness. They could be left-handed or right-handed. I must also say that not all chiral objects are going to be asymmetric. A chiral object is asymmetric if it does not have the plane of reflection, nor does it have a center of inversion. If neither of these things are there, plane of reflection and the center of inversion, then that object will be chiral. So, now this left-handed or right-handed property, I think the best way of understanding this, if we look at our hands, we have a left hand and a right hand, and no amount of rotations I can do to my hands and I can superpose them on top of each other. That is, they cannot self coincide in any possible way. So, chiral objects, the thing is that the images of the left handed version or the right handed versions cannot be superposed. While if an object has a plane of symmetry, that is a reflection plane, then it will not have this property of left handed or right handedness. Now, actually this turns out to be quite an important property, in the sense that if we look at nature, though we may imagine that if we talk about, let us say, chiral molecules, we may imagine that all molecules which are chiral would have an equal proportion of left handed and right handed versions. But interestingly, nature has a bias towards particular handedness. Some good example of those are, let us say, amino acids, sugars. They exist in nature in a particular handedness. And so also many of our medicines today, the active molecule, some of the important medicines are produced with a particular handedness. And if you go back to the 1960s, because a left handed version of a molecule may have the desired effect, while the right handed version of the molecule in a medicine at best may not have an effect, and at worst it could be disastrous. And one classic example of that is the thalidomide disaster. So, thalidomide medicine was considered as a miracle drug in the 1960s for morning sickness. And later on, it was found, after of course disastrous, that lot of births that took place, many birth defects, and it was figured out that the right handed version was the good molecule, the left handed version produced defects. So, that had a pronounced effect on drug testing as well. So, this is what I wanted to just talk about chirality, and it keeps popping up. And now, let us come down to point groups, which are basically nothing but groups of symmetry operations. So, coming back to this group here, which has two elements, 1 and A pi. Now, if I want to make a group multiplication table for this is a very simple table. The first row and the first column is straight away, we can just fill this as it is. Of course, only one cell is left in this, and there is only one way I can fill it, that this has to be identity, so that no element is repeated. But we can also check that basically this means a 180-degree rotation followed by another 180-degree rotation is 360-degree rotation, which is nothing but identity or doing nothing. Now, so here what is the combination rule here? So, Here the elements are actually operations. So, the first element here A pi 180 degree rotation followed by another 180 degree rotation. What is the final result? The final result is a 360 degree rotation, which is basically nothing but the identity operation. So, this is the rule. We will later on see that we can replace all of this by matrices, and then our combination rule would be multiplication of matrices. The second simple point group has the elements 1 and the reflection operation. The group multiplication table for this so 1 sigma, again this is only a 2 by 2 table, this follows as it is. So, in fact, the group looks absolutely the same as for 1 A pi, the two-fold rotation symmetry. Now, let me consider a somewhat bigger group now. So, let me start this with a mirror, I will call that as the mirror M1, and another mirror perpendicular to that is the mirror M2. Now, if I want to look at some geometric shape which would have these two mirrors, could be a rectangle here out here. So, I have the two mirrors M1 and M2. Now, let us take our asymmetric or the chiral object, reflect it across M1 . So, let me call this as object 1 and let me call this as right handed, then this becomes object 2 and the handedness has changed. So, I have denoted it as L. Now, let the mirror M2 reflect the two objects. So, let us reflect the second object first, then second object gets reflected as object 3. Now, since the object 2 was left handed, this will become right handed. I can reflect this third object across mirror 1 and this becomes object number 4 and it is left handed. And you can see that object 1 will also reflect exactly onto object 4 from right handed to left handed. Now, if I look at this diagram more carefully, my object 1 which is right handed goes to object 2 which is left handed and then it goes to object 3 which is right handed. Is there an operation which will take me directly from object 1 to 3? And if so, what is that operation? So, you can see that 1 to 3 both are right handed. So, a simple rotation of 180 degrees will take me from 1 to 3. Similarly, in fact, 2 will take me to 4. So, you can see if you look at this diagram more carefully, there is a two-fold rotational symmetry right where the two mirrors intersect. I can denote that as point A. So, this is at the intersection of the two mirrors M1 and M2. So, I have essentially a rotational operation of A pi right there. So, this tells me that if there are two symmetry operations working, when we combine them, that should generate a third operation, and that is how one forms a group. The two elements of a group, when they are combined through a binary operation, a third element comes which should also be a member of the group. Therefore, A pi will also become a member of this group, and hence this group will have the identity operation, will have sigma 1 reflection from mirror 1 sigma 2 reflection operation from mirror 2, and a fourth one A pi, total of 4 individual symmetry operations present. If one looks at the, so this is a group first of all of order 4, and now let us try to draw the group multiplication table. So, let me just write down the elements. I can fill as before the first row and the first column. Now, let me try to fill the rest of the cells by first locating which combinations are going to produce the identity operation. So, if I look at a reflection through mirror 1, if I reflect 1 to 2 and then reflect back from 2 to 1, I come back from where I started. That is sigma 1. So, what actually I mean is sigma 1, so reflection through mirror 1 followed by a second reflection through the same mirror brings me back from where we started, and therefore, this has to be 1. So, this will be 1. So, identity 1, sigma 2 followed by sigma 2, identity 1, A pi followed by A pi. So, A pi followed by A pi. Well, 180 degree rotation followed by another 180 degree rotation that we have already seen out here would be identity, therefore, this will also be identity. Now, it becomes simpler to fill the rest of the cells. Now, what happens? So, I am using the top column as the first operation followed by the second column or the first row, the elements written on the first row right here. First, that is the operation I do, follow it up by this column out here by those different operations. So, sigma 2 followed by sigma 1 would be what? Sigma 2 followed by sigma 1 is, we have already seen that when two perpendicular mirrors operate, a 180 degree rotation is produced. So, therefore, this is A pi. So, this would be A pi. Let me fill the other columns like sigma 1 followed by sigma 2, well, this is the same result, A pi. Now, it is easy to fill the rest. I have, if I look at this particular row, sigma 1, 1, A pi, only thing that is missing is sigma 2, and you can also verify it from the figure as well, that I do an operation of A pi, follow it with sigma 2. So, if I come to this particular figure, 180 degree operation will bring me from 1 to 3, then I reflect through mirror 2, sigma 2. So, I come from 3 to 2. So, I start from here and end here, and this is nothing but the operation of going from 1 to 2 as sigma 1. So, this is sigma 1. So, A pi followed by sigma 2 is sigma 1. Now, similarly, I can fill the rest, and this group multiplication table is complete. So, I will continue this discussion now in the next lecture. Thank you.